It is generally, though by no means unanimously, agreed that science seeks to uncover laws of nature. The reason it's not unanimously agreed is it is occasionally thought that an emphasis on laws of nature reveals a kind of physics bias. And surely laws do figure more prominently in physics than in, say, biology or psychology. Arguably, that's a matter of the complexity of those sciences. The laws are harder to state, harder to empirically test, harder to use. It doesn't necessarily show that those sciences, in principle, work differently. But some people think that they do, that biology explains narratively, and that biology and psychology both appeal to goal-directed explanations rather than law explanations. That's a complicated question, whether you can have sciences that don't make any interesting or important use of laws of nature. It requires more detailed examination of particular sciences than we're going to be able to go into. But it's worth noting that in biology you do have laws, or at least decent approximations of laws, like Gregor Mendel's laws of classical genetics. And in the human sciences, we find quite a lot of laws, mainly in something like economics. That's a highly law-governed, at least alleged science, the law of supply and demand being the best known case. Economics, while we're on that subject, raises a whole bunch of issues about what makes science science. It's highly law-governed, highly quantitative, but the empirical interpretation of economic laws is itself a vexed question. They come up with very precise models, but do they interpret their models in terms of predictions that are tested against the world? That's a more complicated issue than we can quite get into. But you certainly can have laws in the human sciences. Other issues crop up, of course. Now, the notion of a law of nature, like that of explanation and that of causation, these are closely intertwined, has seemed worthy of suspicion to empiricist philosophers. The very terms in which it's expressed have conjured up associations with divine decrees and other metaphysical pictures. If they're laws of nature, who laid them down? The picture is that laws aren't just facts about how things are, which are supposed to be observable and testable and all that good stuff. A law seems to be modeled on this idea that there's a necessity out there in the world. There's this t-shirt with a picture of Einstein describing the speed of light, 186,000 miles per second. It's not just a good idea, it's the law. That's a connection between laws in the positive sense, the sort of things lawyers study, and laws in the physical sense. And the suggestion is that laws impose requirements on nature. And empiricists want to know what the observable output of a requirement on nature is. So for an empiricist like A.J. Ayer, this feeling that laws require things of empirical phenomena is a kind of metaphysical hangover. It's back to this idea, which might be a fine idea, but is not obviously scientific, that God laid down the laws and makes things follow them. And that has seemed metaphysical and hence worthy of suspicion. So laws of nature must be distinguished from positive laws, which is what you study if you go to law school, and also from the laws of logic, which for positivists and many other people are analytic and hence necessarily true. Right? It's an analytic truth or law that there are no square circles, for instance. But the laws of nature are synthetic, they're not true by virtue of meaning alone, and they're contingent. They could be otherwise than they are. So even if you accept this idea that laws impose a kind of necessity on things or events, that the law prevents anything from going faster than light, the decree that would back them up, this idea that God laid down the law, is itself supposed to be contingent, though it makes certain facts necessary. What do I mean by that? Well, God could have set our universe up with gravity being inversely proportional to the cube of the distance between two objects rather than to the square. So the law itself is contingent, even if it makes particular events obey it, given that it's a law. So it's a contingent, necessitating kind of statement. But empiricists like Ayer are really bothered by this idea that laws make things happen or prevent things from happening. So they want to, as we've seen, focus on logic and language to explicate the notion of a law. Most, if not all, laws are of what philosophers call universal conditional form. We've seen that quite a lot. The form is all A's are B's, or take anything in the universe. If it's an A, then it's a B. All copper conducts electricity has been our main example of this. That's got the right logical form to be a law. But logical form by itself is not going to guarantee that something is a law. And some laws, like the law of supply and demand, which asserts a kind of inverse proportion relationship don't appear to have this form, but can be reproduced in that form. All cases in which supply goes down are and relating price and supply and demand, that sort of stuff. They can be assimilated to the all A's are B's form. Singular facts can be crucial to scientific explanation or understanding, but they can't themselves be laws. The location of the center of mass of our galaxy might be very important for understanding a bunch of things, but it's not a law, it's a particular fact. Laws are general, not particular. Now, it is generally, though not as we'll see next time, unanimously agreed that a statement isn't a law of nature unless it's true. Seems reasonable enough. But names can mislead a bit here, because there are lots of statements that are called laws, and, at least strictly speaking, are not really true. Newton's gravitational law gets corrected by Einstein's general relativity, but sort of by tradition and courtesy, it gets called a law, and it can be used in lots of contexts as if it were true. So, strictly speaking, a lot of laws aren't laws because they're not true. And a lot of things that, strictly speaking, are laws get called equations instead of laws. But an equation can have that all A's are B's form, so that needn't be a problem. For empiricists, the most common approach to laws of nature is a regularity account. A regularity account of laws treats them as statements about what always happens. Laws of nature report or describe patterns in experience rather than something above, beyond, or behind the world which explains these patterns. These are empiricist-friendly theories because they say laws of nature just describe what always happens. But a simple version of an empiricist or regularity theory of laws faces devastating problems. The simplest version would say that any true statement that has the right logical form, any true statement of universal conditional form, counts as a law of nature. This is a disaster. The main problem with such an approach is it can't distinguish laws from accidental generalizations. That's the usual contrast. That's a true statement of universal conditional form that just happens to be true, rather than being a law of nature. So even if it's true, the statement, all the beer in my refrigerator is American-made, does not seem to express a law of nature. It says, take everything in the universe. If it's a beer in my refrigerator, it's American-made. It's got the right logical form. And it needn't be perfectly accidental. I might have a habit or a principle that says I will always buy American beer. But it still doesn't seem like a law of nature, even if it always turns out to be true, and even though it has the right logical form. Well, empiricists then need to explain why it's not a law of nature. One suggestion is we can disqualify the law on the basis of its being restricted to just one place. Something isn't a law if it's just about something as small as my refrigerator. That might be too restrictive, though. Remember, whenever we try to restrict bad cases, we have to worry about whether we're going to prevent good cases. And we want to allow for the possibility that some genuine laws of nature hold at just one place. For instance, on the Earth, some biological laws might be laws, but might be, as it were, local laws. Galileo's law of free fall, which turns out not quite to be true, would be a law if it were true, but it's just about the behavior of objects near the surface of the Earth. So the fact that my refrigerator law is about objects near my refrigerator doesn't automatically disqualify it from counting as a law. Vacuous laws, laws that don't have instances, present a similar kind of problem for a regularity account. So let's take the following law. All particles that travel faster than the speed of light are pink. Now that doesn't seem true intuitively, but remember that it's equivalent to no particle traveling faster than the speed of light is non-pink. And that does seem true. So once you realize that a statement like all dragons like jazz is logically equivalent to there are no jazz-hating dragons, you'll see that it's not so hard to admit that all dragons like jazz turns out to be true, courtesy of there being no dragons. Right? So our statement that all particles traveling faster than the speed of light are pink turns out to be true, courtesy of there being no particles traveling faster than the speed of light. Well, the simple way to get around this problem would be to require that there be at least one instance of something for it to count as a law. You would rule out vacuous laws. You require that any statement to be a law of nature must have at least one actual instance. That would get you out of the problem of vacuous laws. But again, as soon as we try to exclude bad cases, we have to worry about whether we'll be excluding good cases. Not all laws that lack instances are illegitimate, or seem to be anyway. The fact that there are no bodies on which there are no forces anywhere in the universe, there's some gravitational, maybe electromagnetic force acting on any given body, does not prevent Newton's first law, which describes how a body on which no forces were acting would behave. That still seems like a law, and an important law, even though it doesn't directly apply to any objects. There are no instances of bodies on which there are zero forces acting. So we're going to need to buttress our regularity account. We're going to need to impose some more conditions to try to avoid these problems according to which things that don't seem like laws end up counting, and if we exclude them, things that do seem like laws get excluded. The most common way to do this involves an epistemic regularity account, and this was A.J. Ayer's approach. It distinguishes laws from other generalizations on the basis of how we treat them. And this approach can handle the problems we noted above, but it's going to face some major problems of its own. So how do we treat laws differently than we treat accidental generalizations? Well, we let laws support counterfactuals. A counterfactual conditional is a conditional that describes what would happen if things were different. So we can talk about what would happen if the people in the studio here were to pull a certain switch, the lights would go off. That's a true statement about how the world would be if things were different. And so we can say that if my pen were made of copper, it would conduct electricity. That's a mark that we think all copper conducts electricity is a law. While we don't want to say, if a German beer was placed in my refrigerator, it would become an American beer. The difference between a law of nature, or a difference between a law of nature and an accidental generalization, is we treat laws as supporting counterfactuals. Similarly, laws, as we saw with Hempel, hold a special place in our explanatory practices. We can at least begin to explain why an object conducts electricity by saying it's made of copper. If you don't buy the covering law model, we're only beginning to explain, but at least we're beginning to explain. But arguably, we don't begin to explain why a given beer was made in America by saying that it comes out of my refrigerator. Right? True generalizations of universal conditional form can explain things if they're laws of nature. But if they're accidental generalizations, saying something came out of my refrigerator does not explain, even though it's true that all beers coming out of my refrigerator are American, that we can't appeal to that statement to explain why the beer is American. If it were a law, we could. Laws are relatively central to our webs of belief, to use the Quinean metaphor. They are not easily undermined by new information or falsified by apparent counterexamples. So if I'm told that this piece of copper was freshly mined, and I've never seen a freshly mined piece of copper before, that's not going to threaten my confidence that it conducts electricity. And that's a mark that I think the statement, all copper conducts electricity, is a law. But if I'm told that I had some friends over and that they brought beer, and there's a brand of beer in my refrigerator that's never been in there before, I'm going to have my confidence undermined that that beer is American. New information threatens accidental generalizations in a way that it doesn't threaten statements we treat as laws of nature. In addition, we treat laws as more readily confirmed or supported by their instances than accidental generalizations are. I don't have to sample that many instances of copper in order to become convinced that all copper conducts electricity. But if you've been to, say, a meeting of the American Philosophical Association, you might have encountered a bunch of weird philosophers, but you're not going to be perfectly confident that all philosophers are weird. You might think there's a normal one out there somewhere. And that suggests that you don't think that all philosophers are weird is a law. All copper conducts electricity is a law. You think we could easily find an exception, even though it's generally true that philosophers are weird. You don't think that gets support from the particular cases in the same way that all copper conducts electricity does. And this actually is how Nelson Goodman originally set up his new riddle of induction, or the GRU problem. His idea was that the GRU hypothesis has the right form to be a law. All emeralds are GRU has the same form as all emeralds are green. But the mark of its not being a law is that it's not confirmed by its instances. No matter how many GRU emeralds we observe, we don't confirm the hypothesis that all emeralds are GRU. If all emeralds are green is a law, it does get confirmation from its instances, and so we increase our confidence with each green emerald that all emeralds are green. So on this epistemic regularity approach to laws of nature, it's a matter of how we treat laws, what work they do for us, that distinguishes laws from accidental generalizations. The major problem this approach faces is it doesn't look like it can make room for undiscovered laws. What makes something a law of nature is how we handle it. And so something, as it were, becomes or gets transformed into a law of nature, courtesy of being treated in a certain way in our theories. And that doesn't seem to do justice to the idea that the laws are, in some sense, admittedly this is metaphorical, but in some sense the laws are out there waiting to be discovered by us, not made or manufactured by us. We think we're tracking something when we get a hold of the laws of nature, not manufacturing it, or at least many people think that. Which brings us to the most sophisticated version of the regularity theory, or this broadly empiricist approach to laws of nature. Remember, on a broadly empiricist approach, laws are going to have to be nothing more than patterns in experience. Laws are going to have to be built up out of statements about the ways in which things happen. So on the systems theory, the laws of nature flow from the deep structural patterns in actual events. We identify the patterns by figuring out the best way of describing the world in a deductive system. This fits the empiricist approach, according to which we can use observation and logic rather than metaphysics to solve philosophical problems. So we have no resources other than our observable evidence and deductive relations. We're not appealing to some relationship out there of a law preventing anything from going faster than the speed of light. All events are separate was the Humean motto. So any connections between events or statements have got to be, as it were, built up by us rather than found out there by us. Connections between facts or events are not present in observation for people in the Humean tradition. And it's not kosher to claim that we can just reason our way to these things. That would be metaphysics. That would be claiming synthetic a priori knowledge. But the systems approach is going to come as close as it can, while retaining these empiricist scruples, to putting laws out there. So let's examine this in a little bit of detail. What do we mean when we talk about the best way of systematizing experience? Best here means the simplest and strongest deductive system. This notion of a deductive system is very like the positivist conception of theories we saw way back in Lecture 7. Theory is modeled on geometry. It's a set of statements that bear logical relations to each other. It's also even more closely modeled on the unificationist approaches to explanation that we saw the lecture before last, deployed for a somewhat different purpose in the philosophy of explanation. So what do we mean when we say a deductive system has the virtue of simplicity? Simplicity is inversely proportional to the number and complexity of the axioms of the system. Right? So it's a nice feature of, say, a geometry if we don't need very many axioms, very many independently accepted statements, statements for which we're not providing a reason. But we want to do this with experiential content, as we don't do it in the mathematics of geometry. So here's a nice simple theorem. Everything happens according to the will of Elvis. Well, we're only positing one object. So far, we only have one theorem. It's a pretty special object. We've only got one argument scheme, which also is good. Right? So everything is to be explained in terms of the argument from Elvis's intentions. Now, you might need a few more independently acceptable sentences in order to flesh out the king's will. You might need to look at song lyrics pretty carefully, try to get some evidence about what Elvis's will is. But there aren't going to be very many independently acceptable sentences, and you've just got this one argument pattern. So that's a nice, simple deductive system. At the other extreme, a list of everything that happens is a very unsimple, a very complex deductive systematization, because it imposes no order. It has no tendency to try to do the most with the least. Strength is the other main virtue a deductive system can have. Strength is a matter roughly of how informative the theorems are, and that's measured by how many statements about the world can be derived from the statements that make up the theory. So a list of everything that happens is a very strong, though not a very simple, deductive system. Why? Because if you've got a list of everything that happens, it includes everything that happens. You can derive everything that happens from that list. The system according to which everything happens according to the will of Elvis scores well on simplicity but badly on strength. It's hard to derive particular predictions from it, at least not without adding a whole bunch of other statements, in which case it loses its simplicity. So as we see, the simplicity and the strength of a deductive system tend to work against one another. It's easy to have a simple theory that doesn't say much, and it's easy to have a strong theory that isn't simple. The laws of nature, according to systems theorists, the most sophisticated of the regularity theorists, consist of all of the true contingent generalizations, all the statements that have the right logical form and are true, that figure in all the best deductive systems. That's the rule. That's a little elaborate. It's easier to see with examples. So the following statement has a good chance of being a law of nature, according to the systems view. There are no uranium spheres that are a mile or more in diameter. Why? Well, our best physical theories, let's assume for the sake of argument, are highly likely to belong to the best deductive systems. Why? Because we can do a lot with a little. To oversimplify it a little bit, Newton's laws of physics unify a lot of phenomena. With a few independently acceptable statements and argument patterns, we can derive a lot of predictions. So if our best science will figure in the best deductive systematization, then we can derive directly, with no other statements, that there are no uranium spheres more than a mile in diameter, because those theories by themselves imply that if you put that much uranium together in one place, it would go boom. On the other hand, there are no gold spheres a mile or more in diameter anywhere in the universe is not a law of nature. Even though let's assume it's true. Pretty plausible that it's true, but who knows? It's got the right logical form, and it's perfectly true. It looks a lot like the statement about uranium. The difference is it doesn't follow from, it doesn't flow out of the best deductive system. You would have to add it independently as an axiom to get it into the best deductive system. And if you add it, you're lessening the simplicity of the system without getting a compensatory payoff in strength. So if it's perfectly true, it nevertheless ends up being something that just happens to be true. And the difference between things that need in some sense to be true and things that just happen to be true is the difference between laws of nature and accidental generalizations that we were trying to get at in the first place. So this is what the systems theorists have in mind when they say that to call something a law of nature is to say that it is a generalization that is true and figures in or flows out of, two metaphors that amount to the same thing, all of our best deductive systematizations of the world. This looks like a promising way of handling the problems that plagued simpler versions of the empiricist approach to laws of nature. Because laws that don't have instances are allowed, but they have to pay their way in terms of the currency of simplicity and strength. So there's no ban on laws that don't have any instances, but all particles traveling faster than the speed of light are pink does not pay its way in terms of allowing us to derive a lot of predictions we couldn't otherwise have derived. While Newton's law, saying that all bodies on which no forces are acting will continue in inertial motion, arguably does pay its way, and so figures in all the best deductive systematizations. Similarly, laws can be restricted in space or time and still count as laws if they pay off in terms of simplicity or strength. So if we get a large payoff in terms of unifying our experience and our theories by talking about laws that hold only on Earth, if they let us derive a lot of predictions using a modest number of hypotheses, then they count as laws. But it's highly unlikely that there are going to be laws governing the behavior of objects in my refrigerator. We would need to posit them independently, and we derive relatively few observational predictions from those independent posits. So even though it might be true that all the beers in my refrigerator are American, it won't be a law because it would have to be added to any deductive system, and it detracts from the product of simplicity and strength in the system. Arguably, this systems approach explains why the laws of nature have the role they have in explanation, why they support counterfactuals. So for instance, if unification provides the right account of explanation, then the depth of a statement in our best theories is a measure of how unifying its force is. And similarly, the right way to evaluate counterfactuals for an empiricist is going to be given by how much havoc it would wreak with our theory if we evaluated the counterfactual differently. So how do we decide what would happen had Oswald not shot Kennedy? Well, the way to evaluate counterfactuals is first we try to keep the laws of nature constant. Why? Because if we change them, huge changes ramify throughout our theory. So we minimize large, widespread violations in laws of nature. Next, we try to make the situation as spatiotemporally continuous with our world as possible. So we could say, had Oswald shot Kennedy, there would have been a black hole emerging in Dallas. Had Oswald not shot Kennedy, excuse me. A black hole would have emerged on the grassy knoll, and all of matter would have gotten sucked into some other dimension or something like that. Experience doesn't directly tell us what would have happened had things gone differently. But there are more and less reasonable answers to these things. And the measure of reasonableness is a matter of how deeply ingrained in our best theories of the world a given statement is. So even though that was an important particular fact, we don't need to change much about how the universe would have gone in order to talk about how things would have been differently in those cases. What we preserve are laws, not facts, even when they're important facts. Because changing facts changes, to resort to the Quinean metaphor, things at the periphery of the web of belief, not things at the center of the web of belief. So when we evaluate counterfactual conditionals, we're asking which possible worlds are close to our possible worlds, to our actual world, sorry. And we do that by asking whether, according to our best theories, the world works fundamentally differently from our world. And so this systems approach solves the problem with the epistemic regularity view, the big problem with the epistemic regularity view, because what makes something a law is not that you and I believe it. We don't turn things into laws by believing them or using them in a particular way. The idea is our best theories, structured in the best possible way, determine which things the laws are. It doesn't matter whether you or I believe that things are that way. What matters is the deductive relationships that hold among them. So it's got a kind of objectivity. What's nifty about the systems view is it makes laws depend on the best patterns in experience. But best here doesn't mean best as judged by you or I. It means best according to a standard of maximizing simplicity and strength. So it's as objective an account of the laws of nature as an empiricist view is going to be able to get, because all the empiricist has to go on is patterns in experience and deductive relations that hold among them. So though we're far from having a best deductive systematization of our view, of our theories, and it's not clear what it would look like if we did, this approach can build laws and hence explanation out of mere deductive relations. On this approach, to say that the laws of nature forbid something from happening is not to say there's some metaphysical relation of forbidding out there. It's to say the best version of our best theories forbids this thing from happening. And so this builds in as much mind independence for the laws of nature as you're going to get if you're going to insist that laws have to be built out of mere patterns in experience and deductive relations. So remember, Hume had made causation in here, in our heads, rather than out there. There's no necessity of the cue ball moving the 8-ball. The necessity is in our thinking about cue balls and 8-balls. Similarly, the systems approach treats laws and causes as in here in the sense of in our theories rather than out in the world. But it's in here in the sense of an idealized version of our theories. And so it's independently of what you and I think and our current best theories. And so the regularity or systems approach uses all of the resources available to empiricists to prevent laws from having to be about some kind of cement of the universe, some kind of stop sign that the world gives to particles that try traveling faster than the speed of light. And yet it makes laws found rather than made. We'll look at a competing approach to laws of nature in our next lecture. In this lecture, we take a very different look at what laws of nature might believably be. In our last approach to laws of nature, and throughout the course, we've been more or less assuming a starting point of a kind of Hume-inspired empiricism, according to which observation just presents occurrences. And laws of nature on such a view can only be patterns or regularities in experience. We saw the best shot that this kind of classic empiricist approach can take to laws of nature last time. For empiricists, laws don't say anything different than accidental generalizations do. They are both true statements of universal conditional form. A law and an accidental generalization each say of all A's that they are B's. What makes some statements of true conditional form laws rather than accidental generalizations is that they get used in a certain way or fit into a certain system. It is what is done with a true statement of a certain logical form that constitutes its, as it were, lawfulness, in addition to its truth and logical form. But laws themselves have, as a matter of their content, just relations that are asserted among objects. All objects that are made of copper are objects that conduct electricity. That's a pattern that we can observe in experience, and if we could solve that nasty problem of induction, we're entitled to project that pattern into the future. And so the empiricist credentials of such a view look pretty strong. We're taking observation and we are generalizing it, and then we do something with certain observation statements that allow us to treat them as laws. Or our theories on the systems approach do something with certain statements about observable reality that allow them to serve as laws. And this generalizes somewhat to statements about unobservable objects like electrons via the received view of theories and the empiricist approach to how meaning goes from observation up to the theoretical parts of our theories. Necessitarians about laws, on the other hand, take them to describe not the behavior directly of observable objects, but tendencies or powers, not themselves observable, that explain observable phenomena. On this view, laws have a different logical form than they do for empiricists. A law does not assert a relationship between objects. It does not say of all copper things that they are electricity-conducting things. Instead, it asserts a relationship between properties. It says something like, being made of copper makes for or makes you conduct electricity. It's a relationship between copperness and electricity conductivity. If that sounds weird, it's because against an empiricist background, it is weird. You don't see the property of copperness, at least in the usual sense of seeing. And if we follow Hume at all, we certainly don't see copperness making things conduct electricity. Hume had insisted that experience only gives us one damn thing after another, and that as presented in experience, each event is distinct from any other event. This view insists that some properties make other properties hold. Some things make other things happen. So these necessitarians understand they're going well beyond what the empiricist scruples of somebody like Hume and the empiricist scruples of ordinary philosophy of science permit. They are going behind or beyond observation. But they think they have solid reasons for this. They think that if there are laws of nature, they will not be the sorts of things that can respect these empiricist scruples. So necessitarians admit that experience only shows this piece of copper conducts electricity, that one conducts electricity. At best, experience in a reasonably direct way, with induction and some other friends, can show us that all copper conducts electricity. Necessitarians freely admit that experience does not, in a full-fledged sense, show us that copper must conduct electricity. Nevertheless, they say, if it's a law that copper conducts electricity, we've got a very different kind of statement than just that all copper does conduct electricity. If all we have are generalizations about objects, if all we have are statements of the form, take everything in the universe, if it's an A, then it's a B, then there are no laws of nature. So they insist on going beyond observation because they think it's at least plausible that there are laws of nature and that laws of nature go beyond observation in a way that the traditional empiricist view has trouble with. According to this theory, laws do not describe or report patterns in experience, or they at least don't merely do that. Laws govern experience. Laws don't just say what always happens, they say what has gotta happen. No matter how universal or how true a generalization is, all copper conducts electricity, all the beer in my fridge is American, it doesn't say the same kind of thing that a law says. All right, we're here at the level of semantics. We're not talking about what we do with a statement. We're talking about what the statement says. And for necessitarians, a law says not just that you won't find any non-conductive copper, but that you can't find any non-conductive copper. Because being made of copper means you must conduct electricity. So there's a kind of physical necessity. Remember, we've seen a couple times in this course, necessity comes in various flavors. There's logical necessity or possibility. It's supposed to be impossible in a very strong sense that there be a round square. How many corners would a round square have? And there's different kinds of lesser kinds of possibility and necessity. If I played a one-on-one game of basketball with Shaquille O'Neal, it's no accident that he'd beat me. He's sort of got to win in a certain sense. But here we're talking about an in-between kind of necessity. A physical necessity, such that being made of copper is not a matter of meaning entailing conductivity, but it physically makes something conduct electricity. And empiricists are mystified by this notion of necessity. They think all necessity is linguistic necessity. My dissertation advisor, when he was chair of the department, said the strongest kind of necessity is administrative necessity. It's much tougher than logical necessity. It's much easier to make a round square than it is to convince a dean to do something that the dean says is administratively impossible. So empiricists want to know what we could mean by this idea of something physically rather than logically requiring something else. The idea of necessity or requirement is for them a conceptual notion. Necessity happens within our theories or concepts or language, not out there in the world. Necessitarians, on the other hand, assert that laws, anyway, if there are any, require relationships of physical making. This is the very notion that A.J. Ayer had mocked as a kind of metaphysical hangover. Ayer said the only reason we're tempted to talk this way is this sort of lingering idea that the deity or some force behind nature laid down the laws and said, no, 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 you particle don't get to travel faster than the speed of light. And that, he thinks, is an unfortunate remainder of intellectual history, not a sort of scientific insight. So nothing scientifically respectable could forbid things from happening or require things to happen. Science just talks about what does happen. So necessitarians are talking a different kind of language from our classical empiricists. A necessitarian says that given a contingent fact, it could be otherwise, right? God could have made copper so that it didn't conduct electricity. But given the contingent fact that being made of copper makes for conducting electricity, it is necessary that a given bit of copper does conduct electricity. So there's a contingent truth that makes other truths physically necessary. And it's this notion of physical necessity that empiricists like Ayer claim not to be able to understand. So the challenge for necessitarians is to try to make sense of this notion in somewhat scientifically, if not directly experiential terms. So one of the metaphors that Fred Dretske, one of the leading necessitarians, appeals to is legal. And remember, this was the very kind of metaphor that Ayer had mocked. That to talk about a law of nature sounds like a kind of decree. And science doesn't study decrees that somehow linger behind the natural world. So, in Dretske's model, the Constitution needn't have required that the president consult Congress before declaring war. The Constitution is contingent on this. It could have said something different than it does say. But given what it does say, it's no longer discretionary for the president. The president must consult Congress before declaring war. The Constitution requires it, makes it happen. That's the model here. Something in nature makes something else in nature happen. Like the systems approach, the necessitarian approach has certain virtues because it makes laws of nature robust in a way that the simple regularity accounts, according to which a law of nature is just a pattern in experience, couldn't distinguish laws from accidental generalizations. So the necessitarian account can handle the problems that plagued the simple versions of regularity accounts. So for instance, vacuous laws, laws that don't have any instances, looked like they counted as genuine laws of nature on a simple regularity account because they were true statements of the right form. So it was trivial that all particles traveling faster than the speed of light are pink turns out to be true on a simple regularity account. For a necessitarian, that's no law of nature at all because of how demanding the notion of a law of nature is. For a necessitarian, a law says that the property of traveling faster than the speed of light necessitates the property of being pink. And that clearly is false. Now, empiricists are going to want to know how we know that that's clearly false. We'll come back to that kind of worry. But it's not a law. We have no problem excluding it from being a law if we're necessitarians because it doesn't fit our conception of what a law is. There's no relationship of making between the property of going faster than the speed of light and the property of being pink. So because this is a demanding conception of laws, we're generally not going to have problems excluding flimsy-looking apparent laws. That's a problem that plagues simple regularity views, not demanding necessitarian views. Their problems are going to come from the other side, as it were. Like the deductive systems approach, the most sophisticated version of the regularity view with which we ended last time, this view will permit laws that don't have instances if they pass the stringent test. There probably are no objects in the universe that actually slide down frictionless planes. But if there were any, they would meet a certain sort of law because the property of being an object sliding down a frictionless plane does necessitate certain claims about how an object moves. So even if the property is never fully instantiated, there can be a law because there's the right sort of relationship between the property of being on a frictionless plane at a certain angle, of course, with a certain motion, and obeying certain laws. Similarly, if the universe were Newtonian, which it isn't, being inertial necessitates having zero acceleration. There's the right sort of relationship between the properties. And so laws that don't have instances can still be laws on this view because laws are not directly about objects at all. They're about properties that objects have. So on this view, there's relatively little problem distinguishing laws from accidental generalizations. Being made of uranium necessitates, requires being less than a mile in diameter. Because you'll blow up if you try, as it were, to be uranium and more than a mile in diameter. But being made of gold does not require being less than a mile in diameter. It might be the case that nothing is both gold and less than a mile in diameter, but it's not required to be the case. And so the former is a law and the latter isn't. Now it's clear on this kind of a view that laws are discovered, not made. The systems view has a very interesting position on this issue, right? Laws are not made courtesy of any actual theorizing we do, but laws do fall out of our best possible theory. So they're kind of on the border between being made by us and discovered by us. The necessitarian view takes a clear stand on this. The law is out there. It's a metaphysical kind of critter, and we discover it. These views are metaphysically and epistemologically ambitious. They refuse to constrain themselves within the limits of what experience more or less directly shows. And they think they're entitled to do this because of the payoff for good theorizing of discarding these constraints. So these relationships of necessity, of one property making another property obtain, explain, for instance, why laws support counterfactuals. On the regularity view, a law is something like all copper conducts electricity. And it's not clear how we get from all copper does conduct electricity, which is a statement in the indicative mood, it's a statement about what happens, to a statement, if this pen were made of copper, it would conduct electricity. So empiricists say that a law does support a counterfactual, but they don't have much of a story about how the law supports a counterfactual. We talked about this a little bit last time. Their best explanation here is counterfactuals are to be evaluated in terms of a kind of nestedness or importance in our web of belief. But the necessitarians want to point out that the law is a statement about what always happens in the world, right? All copper does conduct electricity. The counterfactual is a statement about what would happen in a different possible world. And there's an inferential move there that's a little tricky for regularity theorists, empiricists, to explain. The necessitarians think they have a much easier time here. It's easy to see how we can get from being made of copper, requires, necessitates, makes something conduct electricity. That does seem to imply if this pen were made of copper, it would conduct electricity. Because we've got the premise that copperness makes for, requires conductivity. Relations between properties carry across possible worlds. Any world in which something is copper is a world in which it conducts electricity, if copperness carries with it conductivity. And this same necessity explains explanation. Necessitarians think that empiricists or regularity theorists have a hard time explaining why explanation works. Let me see if I can make that clear. The fact that all copper does conduct electricity implies that a given piece of copper will conduct electricity. But to imply is not yet to explain. Even to be implied by the best system of generalizations is not yet to explain, according to a necessitarian. The best system of generalizations just says, according to our best theories, this sort of thing always happens. That's all the explanatory oomph, that's all the explanatory juice that an empiricist can have. And a necessitarian says that's not enough. We need more for laws, we need more for explanation. Being deduced from something, even being deduced from a lovely generalization, doesn't show why something is true. It doesn't explain. Being deduced from something won't explain you unless you're being deduced from something that already has explanatory force. So for instance, if I said every marble in the universe is red, that doesn't imply that I can't find a non-red marble. It implies that I won't. But laws of nature make claims about what must happen. It doesn't just say I won't find some non-conductive copper. It says I can't. And that's a very different kind of claim, one that goes farther beyond experience than the empiricists are quite willing to bite the bullet and admit, according to necessitarians. So for a necessitarian, laws explain precisely because they are not generalizations about what always happens. They are much stronger claims about what must happen. And the necessitarians think we should get over that and discard the empiricist scruples. So this controversy between the systems approach and the necessity approach raises deep issues about what is fundamentally explanatory. Is it enough to say of something that it's the kind of thing that always happens? Or to really explain, do we have to in some sense say this sort of thing must happen? And there are costs and benefits to each approach. Empiricists and necessitarians have strong disagreements about the epistemology and the metaphysics of a notion like necessity, of making happen. Empiricists will raise the epistemological issue. How can we ever see when something makes something else happen? You're bringing in some kind of Platonic forms, some notion of a thing called copperness that must have some weird kind of existence in some Platonic heaven or something like that. We shouldn't be taking a notion like that scientifically seriously. We should require that science constrain itself by what it sees. They want to know how we can tell when we see something make something else happen or necessitate something. Any relationship of making has got to be grounded in some fact about what actually happens, according to empiricists. Counterfactuals have to hold in virtue of something. Copperness making for conductivity has to hold in virtue of some more basic fact. And the way they would press this point is saying, we know, at least sort of, what grounds the must in the president must consult Congress before declaring war. It's some kind of sanction, the Supreme Court will slap the president on the wrist, or the president won't get reelected, or something. There's got to be some basis according to which the must holds. And notice that's back to that metaphysical hangover idea that musts can only be some notion of decrees, a lawgiver or a sanction. So empiricists think that laws cannot float free about particular facts about what happens. Necessitarians think that To say that something is a law is to say it imposes requirements on what can happen, and that goes well beyond what does happen. Empiricists don't want us in science to be going that far beyond what does happen. The empiricist will maintain that we have to build our laws and our conception of what's physically possible. What would be the case if the laws of gravitation were different? All of that's got to be grounded pretty tightly in what's physically actual. One way of making this point is to say any two worlds that have the same facts have got to have the same laws. The idea is, if the laws can outrun the facts, we'd have no way of factually testing laws. We'd be slipping into metaphysics in the pejorative sense. The laws would outrun any factual constraint on them. So there's no change at the level of laws without some change at the level of more basic facts. The necessitarian is going to reject this requirement, though. The necessitarian is going to say, isn't it possible that the facts about what actually happens are insufficient to determine the laws about what can and can't happen? So imagine there are two particles that are extremely rare and have never been studied. They have never interacted and they never will interact. There is no actual fact about what will happen when they interact, but isn't there room for the idea that the laws of nature tell what would happen if they ever were to interact? They think the ambitions of science push it beyond the kinds of constraints of the possible by the actual that empiricists require. So there's deeply competing intuitions about whether science is constrained by all of the actual facts, or whether science's need to explain, to impose order and laws on things, requires it to stretch evidence about what actually happens into claims about what could and couldn't happen, or what would happen if things that never will happen were to happen. The necessitarians make a conditional claim. If there are laws, there are true statements about relationships between, say, copperness and conductivity. These things go way beyond observation. But if we can't make legitimate claims like that, then there are no laws of nature. And so they rest on the intuition that science can discover laws of nature. And so they find empiricism timid in its unwillingness to go beyond observation and say we can think our way on the basis of observational evidence to facts about what would happen in different circumstances than the actual ones. Which raises the question of whether, in fact, there are laws of nature. And an important related argument offered by the philosopher of physics Nancy Cartwright emerges here. She suggests either that the laws of nature are false but can be used to explain things, or that they're true but are useless for explaining things. It's an unpalatable dilemma. What does she mean? Our most fundamental laws, she says, don't describe the actual behavior of bodies. The law of gravitational attraction, put forward by Newton, only says how bodies would move if only gravitational forces were acting on them. But that's almost never, if at all, true. There are generally, say, electrical forces acting on bodies. So almost never will we be able to say of an actual body that it will obey this law. For the law to be true, it would either have to be tremendously restricted. It would have to apply to only those bodies on which only gravitational forces are acting, and there might not be any such bodies. Or the law would have to be what philosophers call hedged, protected by a ceteris paribus clause, an all other things equal clause. So we can make the gravitational law come out true, but the strategy we use to make the law come out true threatens to rob it of any application and of any explanatory power. We need the law to apply to bodies if it's going to explain what happens with their motion. And since all other things are hardly ever equal, a law that just says, here's how bodies move, when, according to the gravitational force, all other things equal, doesn't tell us much about the actual behavior of bodies, since all other things are hardly ever equal. Cartwright thinks her approach is friendly to a necessitarian construal of laws. On her view, laws of nature, or laws of physics, don't describe what actually happens. They describe tendencies or powers that underlie or explain what happens. The gravitational law does not talk about the actual motion of bodies. It talks about gravity's tendency to produce motion in bodies. And that is not itself a directly observable thing because they're usually interfering forces. So if the law were true about observable objects, it could explain them. What it's true of is not about the observable behavior of objects, but tendencies of objects to behave in certain ways. And the tendency is not the behavior. We saw this way back when we realized that fragility, a tendency or disposition property, doesn't reduce to actual instances. It's something behind the instances that explains the instances. It outruns experience. Now, Cartwright's opponents have a few options available to them. They can try to say that the laws describe actual things rather than powers or potentialities or tendencies. The actual thing would be a component force. Now, what's the difference between saying that a gravitational law describes a real component force versus saying it describes a tendency for bodies to behave in a certain way? Cartwright's argument, which is enormously controversial, says that you can't treat component forces as fully real. Because if they were fully real, they would be forces in addition to net forces. You'd be double counting your forces. Net forces explain how objects actually move, but net forces are products of multiple tendencies of objects. The way an object actually moves is a product of a bunch of forces acting on it. But you don't want to treat each of those forces as a different thing on top of the net force. But many of Cartwright's opponents think you can find a way, it gets metaphysically a little tricky for our purposes, to count a component force as a thing that's not an additional force that has to be added on top of the net force. I think there's a more interesting approach here, which is we can use context to preserve the truth of the unhedged law that here's how an object behaves if only the gravitational force is acting on it. So if I'm moving out of my house, I can say my house is empty. And if you and the real estate agent come in and say, no, your house isn't empty. Look, there are light bulbs in the fixtures. Well, there's something in my house, and in a certain sense, if there's something in my house, it's not empty. But what counts as a thing in the relevant sense is specified by context. To say that your house is empty in the real estate context is to say it's got no furniture in it. It's not to say it's got no air molecules in it or light bulbs. Similarly, you don't falsify a law like metal bars expand when heated when you point out that if somebody is hammering on both ends of the metal bar while it's being heated, it won't expand. The law still holds. What counts as holding is specified by context. You don't falsify a law by saying that other things can override or impede it. So in that view, gravitational forces have the effects they have. Maybe they describe tendencies, maybe they describe actual behavior, but what the gravitational law says is specified by a context in which the theoretical statement is connected to observation. In the same way that whether I've said something true or false when I say my house is empty depends on whether I'm doing a bizarre physics experiment, in which case it's got to be a vacuum, right? Or whether I'm just showing my house to a prospective buyer, in which case light bulbs don't count as falsifying the emptiness of the house. What really matters here is this is our deepest take, so far anyway, at the tension between science's urge to constrain itself to the observational evidence, to not make claims that themselves cannot be cashed out in experiential terms. That's what stands behind the empiricist view. You never see anything having to happen, you only see it happening. And so they say, if there are laws, they'd better obey these empiricist constraints. A law has got to be some kind of pattern in experience or something we can deductively build up out of a pattern in experience. But there's an equally genuine competing strand in science, which says science explains, it explores the structure of the world, it talks about how things would be if the universe were different. Science is ambitious. And the ambitions of science suggest that something like a law of nature doesn't just talk about what does happen, it talks about what must and what cannot happen. And if that's the legitimate role of scientific claims, then we might have to jettison the idea that science is strongly constrained by observation of what does and doesn't happen. This tension, we've seen it recur in talks about meaning and about evidence, and we're going to see it throughout the remainder of the course, because these are both internal, legitimate aspirations of science, deeply difficult to reconcile with one another. And we'll turn to a new kind of metaphysical problem here in our next lecture about whether and in what sense things like biology might reduce to physics.